Hello, welcome to a new mathematics lesson. Today we are going to show a curious application of the ratio theorem. We have a previous lesson where we showed that for a triangle OVA, defined like the one in this picture, we can find a vector P that locates a point P between the segment A and B in a proportion lambda mu, right? So that is what the ratio theorem is about. We wonder how can we express this P vector in terms of A, B, lambda, and mu, the given proportion of division of the segment AB, right? So I invite you to see that lesson first before watching this video to understand how are we going to use this ratio theorem to calculate the centroid of an arbitrary triangle ABZ, right? Well, of course, here we have three vectors that define the position of the vertices of the triangle, right? So we first need to say that, the centroid is defined as the point of intersection of these segments AF, BE, and CD, where, for example, the point F is dividing the segment BC in a proportion 1/2, 1/2. I mean that, it is the middle point, right, between B and C, and of course, it is the same with E and with D. So the proportion lambda mu in these points will be 1/2 and 1/2, right? So, for example, we first are going to be interested in finding a position vector for D, right? That now it is easy to calculate using the ratio theorem, right? Because we do know what is the vector A, what is the vector B, and we know the proportion of division of the segment AB by D, right? So if we look to this triangle over here and we use the ratio theorem, we can see immediately that the vector D can be defined as 1 divided by 1/2 plus 1/2, and then times. And let's see, if we want to express P in terms of lambda, mu, A, and B, we first see here that mu is multiplying A, and mu is the proportion on the side of BP, right? So in this case, we may need to use this 1/2 to multiply it by A, and then this 1/2 to multiply it by B. But in this case, looking at on both sides is 1/2, well, there is no difference. But you should know that this is the corresponding quantity to multiply the vector A. So we will have here 1/2 times A plus 1/2 times B, right? So with this, we can say that D is equal to 1/2 times A plus B. Okay, perfect. So I think that with this, we need to define another vector that is going to be on the segment CD, because the centroid is located between the points C and D, right? So we are going to be interested in finding a position vector of an arbitrary point between the segment CD. Let's call it R1, maybe here, so that R1 is dividing the segment CD on a proportion maybe mu and then 1 minus mu, right? Because we know that the sum of the proportion or the ratio values need to be equal to 1, right? So mu plus 1 minus mu is equal to 1. So that means that R1 is dividing the segment CD in that proportion. So again, if we use the ratio theorem to define R1, we will have that this mu multiplies the vector that is defining the point on the other side, which is D, right? So it will be mu times D, and then plus 1 minus mu times C, right? And then this multiplies, 1 divided by mu plus 1 minus mu, but that is, of course, just equal to 1, right? So we are not going to write that. Okay, perfect. So now we have a vector that is parameterized with the a parameter mu, and well, that vector can be equal to the vector of the centroid, but not for now, right? We still need to find another vector, right, but in another segment. So how are we going to do that? So first, we can do like the same step, but now instead of doing it with the point D, we are going to do it maybe with that point E over here, right? So just by following the same step before, we can see easily that E is equal to 1/2 times A plus C, right? Recall that A and C are the points that define the segment AC, that is being divided by the point E. Okay, perfect. So again, we are going to look to a segment that is being created by the point E, but now maybe with the point B, right? So we have the segment AB, just as before we had the segment CD. Now we are looking to the segment EB to define a vector that is going to be always on that segment, parameterized with the ratio maybe lambda 1 minus lambda, okay? So that there will be a point where R1 and this new vector R2 are going to match. And that point is, of course, the centroid that we're looking for, right? So the main idea here is to find the values of lambda and mu so that R1 and R2 are equal. And then we are going to be able to express R1 and R2 in terms of A, B, and C so that we get the vector that we want. Perfect. So again, I think that we need to use the ratio theorem to define R2, right? So let me make another draw to watch it more clear. Is something like this. If this is the point E, this is the point B, this will be the origin, right? Then this will be the vector B, the vector E, and then this will be the vector R2, so that this is lambda 1 minus lambda, right? So in this picture, I think it's more clear to see that we can define R2 in terms of A and B as follows. It will be, well, 1 divided by 1 minus lambda plus lambda, but that is equal to 1, and then it will be lambda times E plus 1 minus lambda times B, right? Yep, so let me just write it again in a more fancy way. So, yeah, I think this will be R2, right? Okay, perfect. So what we are going to do first here is notice that we are not interested in expressing the answer in terms of E and D, right? So I think we need to disappear those variables. And that's why we found these two equations. So we are going to plug these values into these R1 and R2 to see what we get. So R1 is equal to mu times D, but D is equal to 1/2 times A plus B. And then we have plus 1 minus mu times C, right? That's okay because we do want our answer in terms of C. And then we have that R2 is equal to lambda times E, but that is 1/2 times A plus C, and then plus 1 minus lambda B, of course, from this that we have here. So again, like we mentioned, we are interested in the point where R1 and R2 are equal. That, looking to the picture, we see that is the centroid. So obviously, we are going to set these two things to be equal. So what are we going to get? It will be mu divided by 2 times A plus mu divided by 2 times B plus 1 minus mu times C. And this is going to be equal to lambda divided by 2 times A plus lambda divided by 2 times C plus 1 minus lambda times B. Okay. So looking that we have a vector equation, we have the sum of three vectors in both sides of the equation. The coefficients of each vector have to be equal, right? Just for this equation to hold. So we have that this coefficient needs to be equal to this coefficient. Then this coefficient needs to be equal to this other coefficient. And then this one needs to be equal to this one over here. So what can we do? From the blue coefficients, we have that mu is equal to lambda. And then maybe from the orange coefficients, we have that 1 minus mu is equal to lambda divided by 2. But mu is equal to lambda, so this is equal to mu divided by 2. So we have that 1 is equal to mu divided by 2 plus mu, which is equal to 3 mu divided by 2, so that mu is equal to 2/3. And then looking that mu is equal to lambda, we have that lambda is also equal to 2/3, right? Okay, so going back to R1 or R2, remember that these are the vectors that when they are equal, well, they locate the centroid of the triangle, right? So in this case, for these values of mu and lambda, it doesn't matter what vector we take. Both of them will match with the centroid of the triangle. So we need to take these values into any one of them to see what are we going to get. So for example, in R1, we will have mu, which is 2/3. So 2/3 times 1/2. Remember that here is R1. This multiplies A plus B, and then plus 1 minus mu, which is 1 minus 2/3 times C. So from here, we cancel these 2's. And from here, well, we get that this is 1/3. So we get that R1, which is equal to the vector of the centroid, equals to A divided by 3 plus B divided by 3 plus C divided by 3. So this can be seen as 1/3 times A plus B plus C. Okay, perfect. So with this, we have found the vector that locates the centroid of a triangle ABC, where, of course, A, B, and C are the vectors that locate the vertices of the triangle. Okay, perfect. So I think that this will be the final formula for the centroid. I think it was a nice application of the ratio theorem, and I think that's a good moment to finish the lesson. Thank you so much for watching.